Question 1 is a very standard kind of question where they give you a bunch of different experiments with different initial concentrations, different starting concentrations of the substances reacting, and then the initial rate, meaning the rate at the very beginning. And the idea is to look at what the relationship is between the changes in the concentrations and the changes in the rates. So you've got to be very confident. These are very common questions. You've got to know absolutely how to approach these. So in this case we've got two reactants, hydrazine and nitrogen monoxide, and if you compare the first two experiments you can see that the hydrazine concentration is the same in both. So the rate is different, and that can't be anything to do with the hydrazine because there was the same concentration in both, so it must just be down to this one. So we can look at the size of that change and say, right, the NO concentration, that was trebled. Okay, so 3 times increase in the NO concentration, but when we look at the rate change, that wasn't just trebled, that actually went up times 9, which is times 3 squared. And so that tells you that the order of reaction is second order because the rate depends on the square of the concentration. Okay, so we need to write something like that down. So we say it is second order for NO because when the NO concentration is trebled, the rate increases times 3 squared, or times 9. Okay, times 9. Okay, and that's enough to say yes, that's clear evidence that it's second order. Now, getting the order with respect to hydrazine is a little bit more difficult because ideally what we'd want is an experiment where only the hydrazine changed and the NO stayed the same, but you can see we haven't got that because the third one is the only one where the hydrazine concentration is different, but you can see that the NO concentration is different from either of these other two. So when you get this you have to be a bit cleverer and you have to take account of both of these changes. So if we compare the first and the third, just because the numbers are easier, you could do it with the second and third, but it's just a bit trickier. So if you compare those two, you can see that both concentrations have doubled. But we know what effect doubling the NO will have because we've already worked out that the reaction is second order with respect to NO. So what we know is that that will go up times 4 due to the nitrogen monoxide concentration doubling. So it's times 4 due to the NO concentration, and 4 times that is 5.48. And then we just look and say, right, well, what else has changed as a result of the fact that we've doubled this as well? And you can see actually the answer is nothing because there's no further change in the rate. Okay, so that overall increase of times 4 is entirely due to the NO concentration, and there's no change due to N2H4. So that's how you work it out, and in your explanation you don't have to go into huge detail, but it needs to be clear that that's how you've approached it. You can't just say, oh, N2H4 has no effect on the rate, therefore it's zero order, because they will think you guessed. So you have to say that when both concentrations change, the change in rate is entirely accounted for by the NO, which is second order, which means that it is zero order for N2H4. Okay, so again, that's enough of an explanation to make it clear that you took account of the fact that both concentrations changed, that you knew what to expect for the NO because you've already worked out its second order, so that doubling should quadruple the rate. And that's all that happens. The rate actually does quadruple, and that's all that happens. So the fact that we've doubled the N2H4 as well has had no further effect, and that confirms that it's zero order for N2H4. Next, it asks us to write down the rate equation. And the rate equation is always of the form rate is equal to K. That's a lowercase k, meaning the rate constant, times some function of the concentrations. And in this case we know it's zero order for N2H4, which means it just doesn't appear in the rate equation. If it's zero order, that means it has no effect on the rate, so it's not in the rate equation. But the NO is in there, and we know it's second order for that, so it's K times NO squared, and that's the rate equation. And then it asks us to find the value of K, which is the rate constant, and also to work out what its units are. So the first thing to do to work out the value is to rearrange this equation to get an equation that says K equals. And to do that, what we have to do is to shift things around here to get K on its own. And if you don't find these algebraic rearrangements easy, remember that this is the term we want to get rid of, and these terms slide diagonally from one side of the equation to the other. So this one is going to slide like that, and that will give us the new form of the equation, which is that the rate divided by NO squared is equal to the rate constant K. You should write that first before you put any numbers in. That's really important, and a lot of people are very reluctant to do it. They just want to get the numbers stuck in straight away. But the problem is, if you get it wrong, if you just make a calculator error, for example, if you haven't rearranged the equation, you're probably quite unlikely to get the marks for working. So much as you don't want to do it, you have to do this algebraic rearrangement first, and then put the numbers in. And this is where there is a nasty trap in this question, because you can just take numbers from the table. So on the face of it, it's very easy. You say, right, choose any one of these experiments. So if we choose the first one, we say, right, that's the rate, these are the concentrations, plug the numbers in, and there you are. Except that there are these terms which you had to notice. Okay, that number is not the rate, that's the rate that's been divided by 10 to the minus 5. That's the concentration that's been divided by 10 to the minus 3. So you must always look for those corrections in any table of data and on any graph looking at the axes, because these are very common in scientific data, and so in the exam they will expect you to look for them and to correct for them where appropriate. So if we choose the first experiment and we're going to put the numbers into this equation, we say, right, the rate is actually not 1.37, that's after it's been divided by 10 to the minus 5, so we have to multiply by 10 to the minus 5 to turn it into the original number, to, if you like, undo that correction that was made. So we say that's equal to 1.37 times 10 to the minus 5 is the rate. And the concentration, NO squared, well, the concentration of NO is 2 after it's been divided by 10 to the minus 3, so it's going to be 2 times 10 to the minus 3. So you just do the opposite of what the correction has been. So it'll be divided by 2 times 10 to the minus 3, but don't forget it's got to be squared. It's very common to forget to use these powers, but it's NO squared, so it's that number squared. So again, write that expression down and then calculate it, and you should get 3.43 if you round it to 3 significant figures. Don't round it any more than that. If you left more significant figures than that, that would be okay in this question because it doesn't say anything about rounding. And leaving too many figures in isn't a problem unless it tells you how to round it. But putting too few figures in is always going to cost you marks. So if you rounded that to 3.4, you're going to lose the mark. Our final job is to work out the units of this number. So it's well worth your while taking the time to learn the recipe for the units of the rate constant. It's much the most reliable way to do it. So the recipe says that you find this number x, which is the overall order of reaction. and the overall order means that you just add up the individual orders for each reactant. So in this case that's just 2 because we've just got that reactant and it's squared, but if there were several reactants you would add up the individual powers. So if x is the overall order, the units of K are moles to the power 1 minus x, dm to the power 3x minus 3, and then seconds to the minus 1. Or it could be minutes to the minus 1, or whatever the time unit is. Always check that, be careful, but in this case it is seconds. So, as I say, in our case x is 2, so 1 minus 2 is minus 1, so it's moles to the minus 1. 3 2's are 6, minus 3 is 3, so dm to the power plus 3 seconds to the minus 1. And that's your full answer. The next part asks us to complete these two graphs to show how the rate depends individually on these concentrations. So this would be a graph showing how the rate would depend on the hydrazine concentration if the NO concentration were held constant, and likewise this shows how it depends on NO if the hydrazine concentration is constant. So we know that this is the rate equation because that's what we've worked out earlier on, and that says that the rate doesn't depend on N2H4, it's zero order for N2H4. So if the rate doesn't depend on N2H4, it means the rate will always be the same regardless of what we do to N2H4, so we just have to draw a flat line across there. Don't do what I just did when you're doing it on paper. Make sure you do it with a ruler and make sure that it's parallel so that it's clearly flat, because you know they can be quite pedantic. If it looks kind of a bit like that and it looks like it might be sloping downhill or a bit wavy, they might say no, that's wrong. So do it properly with a ruler and make sure it's a flat line. Now for NO, we know that it depends on the square of the NO concentration. So this time it is going to change, and it's not just going to be a straight line, because that would be the first order one where it just depends directly on the NO concentration. If it depends on NO squared, it's like a y equals x squared curve. So it's going to look something like that. Okay, so again, draw it carefully. It must go through the origin, because obviously when NO is naught, the rate will be naught, so it's got to go through the origin there. And just don't make sure that you don't overdo it when you're doing a bit of a flourish on that upward curvature. It's quite easy to do something like that and have it sort of starting to tip backwards, and obviously that would be wrong. So just make sure that you don't overdo that curvature, so something like that would be fine. Finally then, it asks us to propose a mechanism for the reaction, which is consistent with these two things. It's got to overall have steps which add up to that, which is the overall reaction equation, but it's also got to be consistent with the rate equation. And the simple rule that you have to know is that the rate determining step, which is the slow step, the number of molecules of each substance involved in that is equal to their order of reaction. Okay, you've just got to know that principle, that the number of molecules of each substance involved in the rate determining step is simply equal to the order of reaction for that substance. So what that says is that our rate determining step is going to involve 2 NOs, and that's all. No hydrazine, nothing else. Now, when you're asked to propose a mechanism from scratch, much the easiest thing is to put the slow step first and explain to the person reading it that the slow step is the one that controls the rate. So we put the slow step and make it absolutely clear that that's the rate determining step, and that's going to come first. And we know it has to have 2 NO in it, because that's what that order of reaction means, and we know it mustn't have any hydrazine. So it's going to be 2 NO goes to something. Now what it goes to is basically up to you, because so long as your two equations add up to the overall reaction equation in the end, it doesn't matter what you put here, but it's got to balance. You can't just put any old rubbish there, it's got to balance with this. So the simplest possibility, we know we want some nitrogen in the end, and we could make 1 nitrogen, and what that leaves us with is 2 oxygens, so we could say N2 plus O2. That would be fine for a slow rate determining step. So what we've then got to follow that up with is a fast step, which then doesn't control the rate, but it's got to be there to complete the reaction. And we've got to think, well, what do we need to do in that fast step? Well, we've got two things we've got to achieve. First, we've got to get rid of that oxygen, because we can see it's not a product of the overall reaction. So if it's made in the slow step, it's got to be used up again in the fast step. So we can put O2. And we've got to bring in the N2H4, because in the overall equation we needed two NOs. Well, we've already had those, but we haven't had the N2H4 yet, so that's got to come in now. So these are going to react in the fast step. And then as to what the products are, well, it's just the rest of what we need here. So we've made one nitrogen already, but we need another one. So we get N2, and we need the two waters. Okay, and that should automatically balance if you just follow those steps. You can check it to make sure. And then that would actually be enough to get you the full marks. But it would be quite a good idea to then just show that if you add those two steps up, it adds up to the overall reaction equation, because you ought to be doing that to check you've done it right anyway, and so it doesn't hurt to show it as part of your answer. So if we add that lot together, we get 2NO plus O2 plus N2H4, that's adding the two left-hand sides together, will give us N2, 2N2 rather, because we've got one there and one there, plus O2 plus 2H2O, and then generally there'll be something to cancel, and in this case you can see it's the O2, so that drops out, and we are indeed left with 2NO plus N2H4, which is what it should be, goes to 2N2 plus 2H2O, which is what it should be. So that's job done. It didn't have to be that answer. You could have chosen to make other products here, but you must have those two NOs there in the first part, on the left hand side in your slow step.